Around the 20th century, brewers at the Guinness factory in Dublin, Ireland had a big problem. They used hop flowers to keep their beer fresher for longer, which also added a lot of flavor. But Guinness was having some trouble with variety, in that they had too much of it. See, hops have soft resin, which varies between different batches of hops, and that isn't ideal for making the same beer every time. Guinness wanted to figure out how much soft resin on average was in the hops using a small number of samples, and they wanted to be confident in those estimates, which meant that they needed to figure out how to quantify that uncertainty. I'm Sabrina Cruz, and this is Study Hall, Real World Statistics. Sampling helps save time, money, and other resources. That's really important if you're a massive beer company, but also in general. Like, if I free up my time, I can spend more of it perfecting my parkour moves. Now, as a quick reminder, when we're using a sample to try and infer something about a population, we call it inferential statistics. That's different from descriptive statistics, where we're only describing something about the actual data we have. And we have help when we make inferences about data. For example, we have sample means, which represent the averages of data sets that are independent but have similar underlying probabilities, like say for different acres of hops. Then there's our trusty friend, the central limit theorem, which tells us that the frequencies of sample means tend to fall into a normal distribution. That is super helpful, especially when you need a confidence boost. Nope, not the kind that you get on a Saturday night after a little beveragino. Now, the brewers at Guinness did have some options already before them. Like, if they looked at how many hops an acre of land produces, they could count all the plants and the number of hop flowers on each one in an acre and calculate the mean quantity. Repeat that over and over again, and they'd get a distribution of what an acre of hops look like on average. That's all fine and dandy, but here's the problem. That process is slow. We're talking hundreds, if not thousands of data points from hundreds, if not thousands of samples, and counting even 1 acre of hops is a lot of work. And sometimes sampling every single thing just isn't an option at all. But taking a shortcut also presented problems. The brewers at Guinness were estimating the mean amount of soft resin in the hops with just a dozen or so measurements in each sample. Their goal was to estimate the mean of the whole crop of hops based on the mean in the sample. What they found was that even the means calculated from the samples in the same batch of hops came out different, and after the chemical test, they couldn't use those same hops to brew beer. The problem was that the brewers didn't know how confident they could be in those mean sample values. Like, maybe the true average for the amount of resin extracted from a batch is something like 6 grams. But if you pull out a sample from that batch, it might have an average of only 5 grams of resin, and another one might have an average of 7 or even 8. Both samples could just be a little off because there are limits to what we could measure. But it was also possible that the samples of hops came from groups that really were different from each other, in a way that the brewers didn't know about. And ignoring that possibility could mean making mistakes that would lead to flavor and consistency issues. They needed a way to tell the difference. Something like saying, I'm 95% certain, based on my measurement and sample size, that the true mean is between 5 and 7 grams. So they knew how suspicious they ought to be when a different sample threw up an 8. Enter Guinness brewer and scientist William Gossett. He worked with the infamous statistician and eugenicist Carl Pearson, and they figured out a way to quantify how sure they could be that their sample was capturing the true population mean. In other words, how sure they could be that the hops they happened to look at were representative of all the hops they wanted to know about. The basic idea is similar to z-scores. Here, though, they couldn't use the normal distribution because they didn't have a big enough sample size. The alternative is something called a t-score. With a t-score, we subtract the sample mean and then divide by the standard error, which is a lot like the standard deviation, except instead of just describing a known sample, it makes an estimate about the whole population. We find it by dividing the standard deviation by the square root of the number of data points in the sample, which we call n. Since we're dividing by something that grows as the number of data points grows, the standard error shrinks the more data we have. The upshot of all of this is that by replacing the standard deviation with the standard error, this new t-variable makes its own distribution, one that looks pretty familiar, but it's not exactly the same as the standard normal distribution. It has its own name, the t-distribution. Let's be clear here, this is not a distribution of data. It's a distribution of how likely it is that our sample captured the true population mean. Think of the hops. Guinness wanted to use samples and be confident that those samples reflected the overall vibe of the hops. Basically, it works like this. The t-distribution starts by shifting the sample mean to 0, so values that fall above that mean will be positive and values that fall below it will be negative, just like in our normal z-distribution. A lot of times the t-distribution looks really normal, but it doesn't always. See, the z-distribution is for a whole population, so it's made up of lots of data points. And when we have lots of data points in our sample, like more than 30, the t-distribution looks so normal that we can just treat it like a z-distribution. In the middle, the probability of capturing the right population mean is really high, because we're pretty sure we've captured a lot of the population in our sample. But with smaller sample sizes, it doesn't work as well. Like with a sample size of 10, the t-distribution curve starts to flatten out. That probability right in the middle is a lot lower, meaning we're less certain about the real population mean. And with a sample size of only 1, it gets really flat, because at that rate, there's really no way to know if we've captured the population mean. But we don't actually use the number of data points to figure out what our t-distribution will look like. We use a measure called degrees of freedom, which we represent with the Greek letter nu, or simply df. Those are the number of data points that could vary in a sample and still give you the same statistic. But it comes to basically the same thing. For the mean, the degrees of freedom are the number of data points minus 1. So the t-distribution basically tells us how likely it is that the population mean is the same as the mean we got in our sample. But unless we're sampling the whole population, that likelihood is never going to be 100%. There's always going to be some uncertainty. Luckily, Pearson and Gossett figured out a way to quantify that uncertainty, so we know exactly how confident we could be that our sample captured the population mean. They did it by calculating a range of values where they could be pretty sure the real mean would fall into, and we call that range a confidence interval. It's kind of like how a person's confidence increases after each pint of beer they drink, or how I become increasingly inspired to show off my parkour moves. The catch is, just like everything in life, we can't ask for 100% certainty. A sample will never capture all of the information about the whole population, and the only confidence interval that covers all of the possibilities is negative infinity to infinity. We know for sure that our true population mean lies in that range, but not what it is. Instead, we have to specify how confident we're looking to be in our estimate. The trade-off is that the more confidence we ask for, the wider our range of values will be. In practice, we usually see confidence levels of 90%, 95%, or 99%, which is about where I am after having a few beers and I'm getting ready to show off my parkour moves. That's because those levels offer a reasonable amount of certainty without needing to gather more data than would be practical. Let's say we want to be 95% confident in our interval. This means that if we repeated our sampling process many times, 95% of the intervals we calculate would contain the true population mean. The t-distribution gives us a way of calculating what range of values is consistent with that confidence. For instance, going back to our samples of hops, we can calculate how confident we can be that the mean amount of resin in a sample of hops is the same as the mean for all hops. Or, more precisely, what range of numbers plausibly includes the true mean of the population based on our sample. It's worth noting that in Gossett's time, statisticians spent days doing calculations and then putting them into tables to look up later, which, let's be honest, sounds like it sucks. But we're in the 21st century, so we can use Google Sheets, or whatever spreadsheet software you like best. First, we need to calculate the standard error. Let's say that we have a sample of 12 hop plants with a mean of 5.75 grams of soft resin and a standard deviation of 0.85 grams. The standard error would be 0.85 divided by the square root of 12, which is about 0.25. Next, we need to find the t-value that corresponds to our desired confidence level and degrees of freedom. The degrees of freedom, remember, are the sample size minus 1, so in our case, that's 11. To calculate t-values for various confidence levels and degrees of freedom, the function we want is t.inv.2t, which stands for the inverse of the two-tailed t-distribution. This function takes two arguments, the probability outside the confidence interval, which is 1 minus the confidence level, and the degrees of freedom. So in Google Sheets, we type t.inv.2t and then 0.05 followed by 11 all in parentheses. The 0.05 is because we want a 95% confidence interval, so the probability outside the interval is 5%, or 0.05. The 11 is our degrees of freedom. This gives us a t-value of about 2.2. Now we multiply this t-value by our standard error to get the margin of error, which might be familiar to you if you've ever suffered through polling during an election year. The margin of error does what it says. It's how much we add or subtract from our mean to get our confidence interval. It's basically a well-defined wiggle room of uncertainty. Since our margin of error comes out to about 0.54 and the mean is 5.75, putting this all together, we get a 95% confidence interval of 5.21 to 6.29. And there we have it. That tells us we are 95% confident that the true mean amount of soft resin in Guinness's hop plants is in that range. So a value of 8 grams in a sample would imply that something was off, so they'd need to take a closer look to figure out what's up. Of course, we could have picked a different threshold of confidence for this whole process. If we wanted a 99% confidence interval, we'd get a broader range of about 4.99 and 6.51. It all depends on how much uncertainty you want to trade for precision, like when I want to jump over a parking meter to practice my parkour. Because here's the dirty thing about statistics. Without knowing how confident we are in a number, no matter how perfect our calculation, a statistical measure can be totally misleading or even entirely useless. Think about when officials advise people to evacuate for a hurricane. It's really different if the plausible range of the hurricane being devastating is 1 to 2 versus more like 0 to 6. Taking a single statistic without knowing its confidence interval can leave you missing really important information. Confidence intervals take us into a world where we're really making clear how confident we can be in numbers. So while we can't eliminate uncertainty in data about our world and the decisions we have to make in it, confidence intervals at least give us a tool to measure and manage it, and decide if maybe parkour after a Guinness is a bad idea. Only one way to find out. Oh my god, it's warm. If you're enjoying this series and are interested in taking the full study hall real-world statistics course and earning college credit from ASU, check out gostudyhall.com or click on the button to learn more. And if you want to help us out, give this video a like, tell us about one time that you were overconfident, and smash that subscribe button. Thanks for watching, and see you next time.